So a very good afternoon to everyone. I'm thrilled to be here. And the energy in the room is palpable. It's great to see such young talent gathered here. And it's a great opportunity for me to make the case that it is your time. The 21st century is the cyber-physical age. In light of social, economic, and ecological trend, it is your time. I will make the case. I will also articulate in my talk things I have learned in my 35 years at Silicon Valley. The idea to value model that is today the norm as opposed to when I started as an engineer in 1983. And in light of the idea to value model, I will look at the trends and see some ideas that I can excite you with. And then I will close with a quick overview of my career in Silicon Valley. And by the way, I will have lots of opinion. And I love dissenting opinion. I'm an extemporaneous speaker. If we could have had this in an interactive way, you could have stopped me at any time. But we will have a chance for you to dissent when we get a chance outside. So when you look at the theme, when Guru talked to me about the theme, solve, adapt, and lead, that sums it up. And let's start. When you go into the industry or you go into academia, today, when we are developing an idea into value, we are developing an idea into a product. When I started, I went as an engineer, I had a set of requirements, and I was given a corporate design engineering handbook for reliability, for plastics design, and so on, and we followed that. And we did multiple prototypes in what is known as a waterfall product lifecycle development, and created products. And if you had to add feature at the last minute, it would be disaster. The world has changed. When you go from idea to value, you have to take a holistic perspective. So if you as a researcher or an engineer came to me, and this is a model I created in running HP labs, and you came up with an idea, you will articulate it in light of the trends. And I will ask you, how are you going to take that idea, hone it down, develop it, and scale it? I will ask you how you are going to scale it. I will ask you, how are you going to put this idea into a product? Let's say you came to me with an idea for a sensor. It's not sufficient for me to just have an idea or for you to come with me with an idea of a sensor. You will show how it comes together as a system. If it's a sensor that is going to do something in healthcare, you are going to show me the systemic instantiation and the multidisciplinary components that are necessary. And you will also articulate to me what are the channels available to scale. So as an engineer and a researcher, you all of a sudden find yourself in a multidisciplinary world where your idea manifests itself as a systemic innovation most of the time, multidisciplinary. And you are also asking yourself, how am I going to bring this to market? How am I going to scale it? So you must take an end-to-end perspective and recognize that what you are doing is multidisciplinary. And as you go from idea to value, you are continuously integrating and continuously developing. And you will see this in my story. You've seen this in software world where people are continuously integrating. So even at scale, let's say you create a sensor and you create a systemic innovation. It's in the marketplace. As you learn, maybe you use machine learning, knowledge discovery, data sciences. As millions and billions of people use it, you learn new things. You are going to go back and change and update your system. So it's a world of continuous integration, continuous development. It's a world where even after you release the product or even while you are building the idea, you are getting field requirements. So in this world, last minute feature is not death or disaster. It is expected. So, I am a mechanical engineer. I'm a hardware person. So when I was in Silicon Valley and I realized that the software people are doing continuous integration, continuous development, I found it challenging that how do you do that in hardware? So let me present to you some of the opportunities. And maybe, it's much more difficult in hardware, but how do you live in this world of continuous integration, continuous development? So in this idea to value model, I say that we start with the trends. So you look at the trends today as you go out, as you graduate, you go out. Let's look at the socio-economic trends that are shaping the future. At the end of the day, we are here as engineers because we want to make a difference at the crossroads of people, profit, we want to make money, and planet, social, economic, ecological. So take a look at the trends today. The global population will be 9 billion by 2050. But even more than that, we are seeing rapid urbanization. So you are seeing urban centers becoming more and more populated. Mumbai is 24 million people. Taiwan is 24 million people. Taiwan is 60 times the size of Mumbai. You don't have to go to Mumbai. You just come to Silicon Valley where I live. And what used to take me 20 minutes to go across the bridge to my home now takes me 2 hours. You come to Palo Alto, it's completely jammed. You go to San Francisco, same story. Yet these cities are served by the same supply-side infrastructure. So if you're in San Francisco, you're still getting water from Hetch Hetchy. So the supply-side infrastructure is being taxed. The demand side is growing. And on the demand side, from a population perspective, we are an aging economy. So the developed world is an aging economy. From a human capital perspective, we have a challenge. People who know stuff are retiring. So if you go to Governor Brown's office in California, their office might be worried that all the people who run power plants are retiring. Well, my kids can write lots of apps, but can't build power plants. We don't seem to be teaching people physical skills anymore. So we have a huge problem. The United States has 4,700 cardiothoracic surgeons. Given our population increase and mass urbanization, do you think that is sufficient? How will we scale those 4,700 cardiothoracic surgeons? And people don't want to go into that field. It takes 12 years to become a cardiothoracic surgeon. So you will have to figure out a way to scale them from one to many with robotic surgery, AR, VR. So when you think of AR and VR, you're going to have to think of how will you use it to enhance productivity in light of this demographic shift. Then there are the ecological considerations. We are sucking up on the supply side, not thinking about tomorrow. And then there are the negative externalities. We did things that were beneficial to us in the short term, but now they have become burden to society. We deforested Amazon jungles, took bauxite from there, shipped it to make aluminum somewhere else. Then we made somewhere else, used it here, and then disposed it yet another place. Our supply chain looks very convoluted. We did that because along the way there were subsidies, there were power plants that were polluting, but we just did it because it was low cost. Now we are going to have to pay the piper. We have to pay that all the things we did in the near term have now become a burden. The areas where these subsidized power plants were built, the air is unbreathable. We have ecological consideration. So you as students of electrical engineering must get together with your friends from economics and understand what is the meaning of these negative externalities. All over the place they have become a burden. So in light of socio-economic ecological trends, you have to ask yourself, what is the role of technology? And the way I see it is the following, and you will see a lot of sketches. Being in Silicon Valley, I'm constantly bombarded with bombastic words. Acronyms, end-to-end, cloud-enabled, blah, blah. I can't keep up with that. So I tried to abstract everything to a simple visual. And the way I see technology is as follows. 19th century was about the steam engine or the machine age. The 20th century was about the cyber or information age. The latter part of the 20th century was about connecting people to the internet. But only a third of the world is connected to the internet. 2/3 of the world is still not connected to the internet. And those of us who are connected, we are sucking up energy like no tomorrow. In the morning we have cereal and decide to take a picture and upload it. While you're doing that, think of the available, like Dr. Shroop talked about remembering your periodic table. I want you to remember your second law of thermodynamics. When you take that picture of the bowl of cereal, think of the available energy in the fuel that was consumed to make that electricity. The water at that height of the dam had to drop, and by the time the available energy in the dam, by the time it got to your computer was only 5% of what was available. You're using precious available energy to do various transactions. And so all of us, 1/3 of us in the world are really loving this internet, buying things we don't want, enjoying ourselves. But the problem lies in the 2/3 who are not connected, because in addition to doing frivolous activity, we are also using internet for useful purposes. When I go to India, I get train reservations done in 2 minutes. Sitting on my bus, I take public transit from Fremont to Palo Alto. From my bus, I have Wi-Fi. In 2 minutes, I get a train reservation on a train in India. I just beat a guy who makes $5 a day. He's among the billion people who has cell phone, but he's also among the billion who doesn't have data services. So when he wants his train ticket, he has to go to the train station. I'm not proud of outgunning him. So the digital divide of the 20th century must be closed. You have to ask yourself, is the current IT model that starts at the cell phone, goes through this network to this warehouse scale data center, will this work in connecting the rest of the world? Or does that deployment model have to change? I contend it has to. But today I don't have the time. So I won't talk about the 20th century. It's your job to take care of what we didn't do in the 20th century. We failed to connect 2/3 of the world. Now on the 21st century, there's a huge opportunity. 21st century is the integration of physical system with cyber systems, information systems. You might say it is about taking old infrastructure, connecting it to taking the steam engine and connecting it to information systems, cyber systems. Or you may say it's a modern infrastructure. So you see a picture of an electric automobile, it should look like a Tesla Model S. And so let's take a look at that. That's a cyber physical system. So how do you look at cyber physical system? This is your world. So when you go out there, you will be working on cyber physical systems, the 21st century opportunity. And of course, you'll try to solve the 20th century problem as well. So the way to look at a cyber physical system is at the physical level. Don't start at the cloud. And please don't start at the app layer. Start at the physical layer. So my daughter is an industrial engineer. She got an interview at Tesla, and she works at Tesla right now. And so she said, Dad, I got an interview tomorrow. I said, okay, you know what? Let's whip out the whiteboard in the family room. By the way, the kids in my household call it torture, whiteboarding at the Patel household. So I said, let's take out the whiteboard at the family room, sketch out the Tesla vehicle, personify yourself as the vehicle, and tell me how do you size the motor in the car. So go with first principle, determine the resistance, the rolling friction, determine the wind resistance, feel the wind, look at 25 miles an hour, what dominates at 70 miles an hour, look at the supply side, it's an 80 kilowatt hour battery, how long will it last? And by the way, Tesla wants to build autopilot. What sort of sensors and actuators will you use? Will you use radar, video? What are the sensors that are available in the state of the art? How will you use them? And by the way, if you're going to build a control system, you need actuators. How will you actuate the vehicle? So folks, you have to think of the flexible, configurable, mechanical platform before you think of the cloud. Because if you don't build a flexible system with sensors and actuators, you're not going to have an autopilot. It'll go straight. So you have to think of the flexibility and configurability. You start at the physical level. Then the guys use induction motor. So why do they use induction motor? So you have to understand the physical platform. And then you say, okay, they promise autopilot. So someday with the cloud connectivity, they will continually upgrade the vehicle. And that's what they did. A year later, you see this vehicle. It was built with flexibility. Now it's got auto assist and so on. So when you think of physical platforms or you think of any kind of a platform today, you must think of that flexibility. Because what is happening today is when we build things, we have to build it with those flexibilities so you can upgrade it. Because when you go out there, you will develop algorithms for improving the control system. But that's continual improvement. AI is a field where algorithms will continue to improve. And as they improve, you have to update the hardware. You cannot Tesla can't come out with a different car the next day. So you have to think about, at the get-go, how do you design the physical platform? So that is the cyber-physical world. And so let's look at some of the cyber-physical solutions on the 21st century. In the 20th century, those of us who were connected, we mined tweets from Hollywood and Bollywood, prime ministers and presidents, Ashton Kutcher and Beyonce. But we failed to look at tweets from airplanes. We lost airplanes. We can't even find the airplanes. So when the pitot tube froze at 35,000 feet, could we have told the pilot, forget about the autopilot and just manually fly the plane? If we were following the airplane, could we have helped it? You have to ask yourself. In the 20th century, we failed to manage physical systems. Do you think oil platforms just blew up? Don't you think pressure was building when we have had all these kinds of challenges? So in the 21st century, the CyberPhysical Solutions will focus on gathering data, analyzing, and running things safely, improve productivity in light of socioeconomic ecological trends. So if we were to collect data and do real-time analysis to inform the pilot or to inform the people who are running the factory, the computing will have to go back on the plane. You're generating a terabyte of data on a transoceanic flight. Do you think you're going to stream it all to a data center, analyze it, and tell the pilot? Don't you think the latency is too high? So you have to ask yourself, the computing building blocks will have to be we'll have to re-examine the computing building block. So real-time analysis, whether it is for airplanes or for that robot, the pig in a pipe that's taking video data. So today, we have old aging infrastructure. We have pigs that are traveling in a pipe, these robots. They're videoing the data. We collect that video data, and then we send it off maybe to Bangalore, and lots of people sit in a room, look at video data to look for cracks in a pipe. It's got to be a better way. We'll have to look at the video data, we'll have to analyze it in situ, and we'll have to inform. We cannot just sit and collect data for months and then analyze it. Now that will happen, and we will do historical data mining. For example, we did work and we reported it in KDD, the Knowledge Discovery Conference, where we mined data from cooling towers. So in the 20th century, we mined your buying patterns. We did machine learning to determine what you buy, and let us sell you something you don't want tomorrow. In the 21st century, we will mine data from cooling towers for months, and that historical analysis can happen at the data center. So in our case, we collected data for 6 months, looked at the patterns, and then found the most efficient pattern and ran the cooling towers and the cooling systems given that pattern. And the customer bought it because they saw value. In the 21st century, your conversation with customer will be value driven. The customer will ask, how does your solution save them money? How does it save them energy? And given the savings, the products will be priced accordingly. It's a value-driven conversation. So it's very exciting because in the physical world, to do data mining, machine learning is a very exciting field indeed. And even at home. So as an example, I am at HP. We are selling computing units. My father bought an HP all-in-one. It was interesting. He bought an all-in-one, paid $500, and he got a Magic Jack. Magic Jack allowed him to make free phone calls all over the world. And he noticed that by using Magic Jack, he could get return on investment on his device. That's how people will think. So if he got a return on investment with just a phone call on an USB, shouldn't I, as the chief engineer at HP, think about how can I use our endpoint devices better? Our devices are being built with very good cameras with multiple sensors. So how do I use those devices with sensors and cameras to look at him? Can I have discerned his emotion? Can I do situational intelligence? Can I use cameras in an ICU, intensive care unit, to determine how the patient is doing? Why do I need a sensor? Can I use video information? So when you go out in the field, you are going to be developing algorithms that will use endpoint devices with all these sensors to deliver value to the customer. But then, if those of you who are designing the computer, so the algorithmics people will design the algorithms, but those of you who will go into designing computer have to ask yourself, how do I make it a flexible computing building block? Do I use a CPU or do I use a SoC? Should I use an FPGA and leave that FPGA for future? That's adding cost at the get-go. But how do I build a flexible computing platform just like Tesla so that as your friends who are developing algorithms, they can use that flexible platform to continually update and improve the experience? So edge computing, it's time to revisit edge computing to see what are the computing building blocks. How will they work with the algorithmics? How will you update it? How does the computer become a Tesla vehicle? So it's interesting, the mechanical world, electrical world, all of us who are in hardware, we have to start thinking along this. Because policy-based control system analysis is coming, it's not here yet, and that's going to be critical. So computing at home, think on both on the computing side and on the algorithmic side. And then we hear a lot about AR and VR. And for me, this is an exciting field. So haptic holography is an exciting field. But when I look at these opportunities, I don't think in terms of massively entertainment, which is a great opportunity. I think in terms of some of the trends. What did I say at the beginning? People with knowledge are retiring. We are an aging demography. Can I use AR and VR to improve productivity? So my son is a surgeon. And when he was taught surgery, the doctor told him, can you feel the vessel? Think of when you're doing the surgery, you can't see. Feel the vessel and think the elasticity of the vessel. By feeling the elasticity of the vessel, they can determine what kind of a vessel it is. So can we give touch? So can we give touch so that mechanics, who are few and far between for maintaining airplanes, can maintain it with this AR, VR-like capabilities? So think of AR and VR from a socio-economic, ecological consideration. Think of it for productivity improvement. Think of it for energy savings. Think of it for something useful. Huge opportunity. So I talked so far. I motivated that the 21st century is the cyber-physical world. It's the integration of cyber and physical. I provided examples of edge computing, where edge computing is flexible, and we will be using edge computing to do situational intelligence, emotional intelligence, to provide telemedicine, personalized healthcare, all those kinds of things in light of the trends. I talked about AR, VR in light of the trends. The one thing I did not talk about was in light of these externalities and supply-side constraints, I contend that our production and consumption model will change. I once met Mr. Greenspan, and I asked him, in light of these social, economic, ecological trends, I contend that joules of available energy is the currency, not dollars, rupees, or yuans. So when I look at my laptop, I say that's 9 gigajoules or 200 liters of diesel. I either think in terms of diesel or kerosene. Once you burn it, it's gone forever. We're going to have to wait for dinosaurs to come back. So I like to go back to second law and available energy. So from an available energy perspective, my contention was, my laptop is 200 liters of diesel. If I look at the energy, available energy required for extraction, waste mitigation. So if I have a factory that's causing waste, how much available energy will I need to mitigate the waste? The available energy required in transportation, available energy required in usage, available energy required to reclaim the product. So if joules is the currency, don't you see that the current supply chain is likely to change? So my contention was to Mr. Greenspan that if joules is the currency, do you think design and manufacturing is coming back? So instead of dollars, rupees, or yuans, you think in joules all the time. In my household, when the kids do frivolous transaction, I ask them, how many joules of available energy did you destroy for that transaction? I like you to calculate the amount of energy required to boil that cup of water. Go back to available energy. So if joules is the currency, we have an opportunity. You have an opportunity. The challenge we have as US is trade skills. We don't have the trade skills. We lost our trade skills for various reasons. The community college where I taught decided to do away with machine technology and so on, right? We shouldn't have, but we did. We have lost important trade skills. So we will have to improve automation. Once again, it's a human capital problem. We'll have to use AR, VR, all kinds of techniques to augment those skills as well. In addition to improving the supply side by telling people that it is good to be a carpenter, it's good to be a metal worker, it's good to be a welder. But we also have hope with 3D printing. So, of course, we are in 3D printing at HP, and I see 3D printing as an opportunity to go from art to part. You might see a video where we show a nylon link that lifts up a car. The car is 1,000 kilograms, so it's about 1 kilonewton. 10 kilonewton, lifts up a car and was printed on demand. Now you might say that, well, that the link is structurally sound, it lifts up a car, but it may be more expensive than what I can get in the hardware store. The problem with the one in the hardware store is the hardware store is over-provisioned. You go there are links sitting all on the shelf. Most of them will never be used, and I see them as bottles of diesel sitting on the shelf. So with 3D printing, you can print what you want when you want it, no more, no less. So once again, with automation, with productivity improvement tools, with AR, VR, and 3D printing, do we see an opportunity in a world where we use joules as the currency, not only to have an ecological impact, but as a nation, see how we can drive economic growth? So I want to close with the following, and I want to close with my personal kind of what do I do? I decided to bring this at the very end. So I used to run HP Labs, and my boss, CEO at that time, asked me, Chandrakant, what do you want to do after you've done this job for a while? I said, I want to be the chief engineer of the company. And she likes maritime analogy, so I sketched out a ship. As you can see, I talk in sketches. So I sketched out a ship, and I said that on the bridge, I want to play the role in looking at the megatrends, socioeconomic, ecological megatrends, to determine where we need to go. So in companies where you will go, the C-suite is focused on looking at the megatrends to set the course of where to go. And then I told our CEO that HP, my company, is a multidisciplinary company. So I also want to work in the engine room. The engine room of the company is very rich. We have chemists, mechanical engineers, electrical engineers. We have ink chemists. We have materials engineers. And one thing that should be very apparent to you, given the solutions I talked to you, it must be very apparent to you that these are all multidisciplinary solutions. You cannot do it by yourself. You have to become broad. You have to have your depth skills, but you will have to have your breadth skills as well. And so what I said is, in order to go from idea to value, the model I showed left, in light of our vision and fundamentals and technologies, I want to seek out all the key people that are in our company. So I drew that pyramid. The problem when you go to many of the companies you will work with is there are electrical engineers, there are mechanical engineers, there are a few in various locations in the company. So globally, they are distributed. They are in what is known as silos. So I wanted to go through the silos, and I say, for the company, let's identify all the engineers from bottom of the stack to the top of the stack. So let's start by identifying all the people who work in chip technologies. Let's identify all the people who work in printed circuit boards. So circuit breakers, for example, is one of the groups. So we went all around the world, Bangalore, Boise, Barcelona, identified all the printed circuit board interconnect people. Then the firmware people. Then the data mining, machine learning people, and on and on. So why do I need to get these capabilities? Because if we want to build solutions quickly, we need to look at all the resources we have in the company. When you go out, you're going to have to work with your global pool of resources. And the vision I had was, let's train them and let's get them together to solve problems immediately. So that's the helicopter on the ship. It's a commando-style approach. If there is a solution, let's say in healthcare, that I want to build. I want to do a hackathon in healthcare to build a low-cost solution. In today's world, I will provision these people immediately like a commando team. And my vision is bring them from Barcelona, wherever. So if I need a set of people in printed circuit board design, in machine learning, get them together to go after the problem. I can't think in silos. I can't hire people in silos. So you are graduating to a world where you as a leader are going to have to look across the company. You'll have to go across the silos. You'll have to, as the earlier speaker said, you'll have to have great communication. So there was an awesome talk on leadership. You will have to have those leadership skills to be able to pull these people on demand. So that's what we have done, and that's how we are moving ahead. And so like I said, I want to close with one last discussion or a presentation on what I have, where I have been and what I have done. So one of the things is I mentor a lot of people. And when I mentor people, and it could be you, I ask them to create a visual CV. I don't like words. By this time, you should have figured that out. So I tell them to draw themselves out. And this is my picture. So I start by saying, you got your fundamental depth in history, art, science, mechanical engineering. I don't care. In humanities, in some skills. To me, that's very important. I am a mechanical engineer. I'm paranoid about forgetting mechanical engineering. I keep my physics book from high school, Resnick and Halliday, Sears and Jimansky. I keep Holman's heat transfer book. I keep Reynolds' thermodynamics book. I'm constant. And I refer to them. I teach a graduate class in heat transfer thermal management. I've written papers. I'm paranoid about forgetting what I learned in school. So to me, the depth you start with is the depth you maintain. So on this chart, on the plus Z axis are the subjects I took, and the depth I maintain is the way I maintain it, as the previous speaker said, by virtue of lifelong learning. And then the breadth skills you see are the breadth skills I pick up in light of where I want to go, in light of my values. And those include, various disciplines and various leadership skills in the company. So if you were my mentee, I would ask you to create a visual CV. And you can see I have gone from chip design to disk drive design to data center design to chip design to system design to data center design to city scale resource management. I've gone from nanoscale to kilometer scale. And the reason I went is in light of my values and the trends. So your values are important. Your understanding of the trends is important. It's important to be multidisciplinary. Remember your depth. Garner the breadth. And wish you all the best. Thank you very much.
Thank you. That was good.
Do you have time for questions?
We have time for questions. Please turn on the light a bit first. So I have one question.
Right.
You mentioned about art to parts. Surely we know you're an artist by your sketch.
Right.
So at what age you practice sketching? Because this is really phenomenal. It's really like a piece of art and bring it to technology. So when do you pick up that sketching skill set?
Yeah, so I was crazy about airplanes. And the first airplane I saw was a V-tail Beechcraft Bonanza. How many of you are familiar with that? I guess I see a hand back there. So a V-tail was the first plane I saw, and I was inspired by it. And so I started sketching during that time started sketching airplanes. But I found that I'm an extemporaneous speaker, and I taught for 16 years at a junior college, and I also teach in San Jose State and Santa Clara. I don't prepare my notes ahead of time. I go into the classroom. I use the whiteboard. So I found myself drawing on the whiteboard all the time. And I always tried to teach my students by going back to the basics. So that's how I picked up a lot of the sketching, initially in childhood and then throughout my career, in either talking to the executives. So I do sketches which explain a concept. I also do sketches that can be taken to design. And the reason I use art to part analogy is when I started as a mechanical engineer, I was doing things on the drafting table. Then I learned CAD, Pro Engineer, and so on. I taught CAD. But I see a world where in the future, you will be able to take an artist's work to part. And you as engineers will have to figure out, how do we do the detailed design that we do in the past? Do we really need to do detailed design? Or can we take that art and you produce the tools, the computer-aided engineering tools, so we can go from art to part? In other words, democratize computer-aided design. Everybody can take part in it. That's why I use the terminology art to part as opposed to design to part. I think we will see a world where you will be able to take advantage of the brilliant artists who are around the world.
Cool. Thank you. I'm actually intrigued about your nickname, or so-called your King of Cool. So I'd like to know, how do you get the nickname King of Cool? Can you share with our audience here?
So it comes from, if you can go to that, yeah. So when I started in disk drive business, and the drives were big, the size of a washing machine. 80 kilograms was the mass of the head disassembly. I saw that the drives were becoming smaller. The stiffness to mass ratio was going up. So if the stiffness to mass ratio goes up, the natural frequency goes up. As mechanical engineers, we were always trying to protect the drive. But I felt as the drives became smaller, they'll be easy to put together. So these low frequency vibrations won't bother him. Vibrations at a kilohertz will be a problem. So I said, you know what? This field is commoditizing. So let me get out of this. So I went out for drive business, and that was when I took a reset in my career. I had moved up 8 years. I took a reset and got into chips. And when I got into chips, I recognized that the chips were becoming flip chip, and soon a microprocessor the size of a postage stamp, 2 centimeter by 2 centimeter, 20 millimeter by 20 millimeter, will generate 100 watts. And in order to cool 100 watts, we have to come up with new technology. So I changed from dynamics of structures to a thermal engineer. I had never done a chip package before. I wouldn't know a quad flat pack if it came and hit me on the head. But you know what I told them? I said, I have all my books. I'm going to personify myself as a signal and figure out how do I get out, how many pins do I need. I'll personify myself as a heat flux and figure out how do I remove heat by conduction, convection, and other things. So you see, the principles you learned in school are sufficient. You can remake yourself. So I went from dynamics of structures to chip. And that's how I got the name, because I established the electronic schooling research. I was the one person in HP. And then it grew, and I thought that it's time to get out of that, and I went into systems. And then I said, building is the computer. I got into data centers, and on and on and on.
Cool. All right, thanks everybody. King of Cool, thank you.
Thanks.
Thanks a lot.